everything's going to start to kind of come together. All right, so the different tests of significance, also known as hypothesis tests, are one population proportion, one population mean, two population means, and two population proportions. So proportions are really just talking about percentages. So any data set that involves a percentage is going to be considered a population proportion. All right, so we just want to keep that in mind. All right, so and that's the thing, when you're surveying people, most of the time it's going to be related to percentages. Right, so definitely want to have that in mind when you're considering, first, whether a project is something that you even want to do, but second, if you've already collected some data, or are you dealing with simple counts? 10 people said yes out of 100 people, something like that. Right? If that's the case, then you're dealing with a population proportion. Right? So that would be these cases. Both of them deal with, again, percentages. All right. Morning. So then the other ones, I mean, it's pretty clear they deal with averages, the means. So if you have quantitative data where you have measurements involved, so heights, weights, blood pressures, lengths of time, things like that, that's where the means would come into play. Right? So, but basically most people just kind of remember it as anything other than percentages, right? Because it's pretty easy that way. Right? So the vocabulary that comes into play, this is a universal no matter what type of hypothesis test you're dealing with. You have a null hypothesis and then you have an alternative hypothesis. It's one or the other. Right, so one or the other. All right, it's either the null or the alternative. And a good question would be like, okay, so what's it? What is the it you speak of? It would be the conclusion, the answer to your question. All right. So that answer is either going to be what you've designated as the null hypothesis or the alternative hypothesis, and it's going to be supported by probability. All right. So the null hypothesis, it's stated right here. This is either a statement that's being tested or some understood or accepted value for the population parameter, status quo. The only sign here used here is the equal sign. That part, that last little statement might not mean too much just yet. Same thing for alternative, but everything else, it's related to stuff that we've talked about in the class. But just a reminder, parameter is a measure for the population. Null hypothesis or the alternative hypothesis. Undo. All right, so a measure for the population is really what a parameter is. Right? Because statistics are measures for samples. Right? And so what we want to do whenever we want to conduct the test of significance is make a determination of whether our sample statistics tells us anything meaningful about the population parameters. All right? Because we were talking about different types of sampling last class, and if you have a representative sample, if you have a sample of individuals that you know are representative of the population, then it logically follows that what conclusions you draw about the sample should in some way correspond to the population. All right, it's just a question of what's the connection? What's the, is it a one-to-one relationship? Is it like what happens in the sample is exactly what happens in the population? or is what happens in the sample kind of what happens in the population, right? And if it's kind of, you got to throw a percentage on that. That's the probability. So what are the chances that the sample results are in alignment with the population, right? If it's a strong probability, then we would say that we've drawn a significant conclusion, right? But if it's not, then you know, that would be the end of it. You wouldn't have proved anything, except that you couldn't prove the thing you were trying to prove, right? So that can be kind of a tricky thing to wrap your brain around. But the idea is, you have a question. I mean, just simplify it as much as you can in your mind. You have a question that you're trying to get the answer to, related to people, like people in general. But you don't have access to all people. You have access to some people. So you can collect information about some people. And what you want to do is make a determination of whether that information you got about the some people could apply to all people. All right. So if I polled you all on, you know, your performance in an English class, you know, like what was the last grade that you received in an English class, and you told me the grade that you received, I'd create a distribution and say we'd have this many A's, this many B's, this many C's, and so on. I would have to really consider the nature of the distribution in order to say, okay, all WCC students follow that same proportion, right? Because it is possible that you all received A's in your last English class, right? Could I then say that all WCC students received A's in their last English class? Probably not, right? But maybe your A's, like you all received A's, but maybe what that would tell us is that most WCC students would have received A's in their last English class, right? And so how can I quantify that? That's always going to be the question. How can I quantify that, right? So yeah, that's the ultimate objective here, because the null hypothesis is what we're trying to test, right? So I would, in that case, I would test the claim that a certain percentage of students receive A's, you know, and then the alternative would be something other than that. So either more than, less than, or just a different percentage of students received A's. You know, because I could make up whatever percentage I want because it's my question. I could say half the population received A's, or I could go the other way and I'd say, you know, people are just doing very terribly in English classes, so everybody's failing. Nah, not everybody. Most students are failing. So I would say, as a population proportion or a percentage, more than 50% of the population received an F in their last English class. All right, so that would indicate that most students are failing, right? And so after I run that test, after I run that hypothesis test, it begins the investigation, right? That's not the final analysis. And that's the important thing to understand. The hypothesis test is really just kind of getting the conversation going, all right? Because you can't just leave it there. You know, if you concluded that most students failed their last English class, you wouldn't just bring that to the president of the college and say, hey, guess what? English department sucks. Like, hold on. What was the cause of why most students failed their last English class? So then you'd look at other variables. Now you start getting into amount of time studying. You'd get into attendance issues. You'd get into the level of experience of the teachers, because there's always that. You get into the classroom environment. You know, you start the conversation of, okay, now that we know there's a problem, let's see if we can narrow down a little bit more specifically what that problem might be. All right. So, you know, because you could look at it like, I mean, we're in a class, so, you know, class examples always come to mind. You know, so you do poorly on a unit test, and it's like, and you could look at it collectively. We all bombed it. No, well, you didn't. But let's say that ever happened. If it did, that would be like the first time. But let's say everybody bombed the last unit test. Then that's the beginning of the conversation. So we collect the data, we look at it, and we say, all right, we have, I think, 17 people enrolled in the course. 14 of them bombed the test. Okay, so now we have the what happened. Now we got to get into the why. So then we would perform an analysis on the types of questions that were used. All right, and so that analysis would be data-based. All right, so it's always how could you quantify it, all right? Because you might say question 3 was too hard, and I would say quantify that, all right? So that's the issue. It's always going to be quantify that, all right? So when you're thinking about your studies, you have to have that in mind. How can I quantify this? How can I assign a number to it, a meaningful number, all right? So number 3 was too hard. Okay, so now let's take a look at number 3. How much was number 3 worth? All right, it was worth 10 points. How much work was required? Not much. Okay, so now we're getting somewhere. In number 3, it was a 2-step problem. All right, worth 10 points. You screw up one step, you already lost 5 points. All right, so now we're talking about, okay, the question wasn't too hard. The amount of points assigned to that question was inappropriate. All right, so now we would say, okay, well, what if that 10-point question was a 4-point question? How would everybody have performed? So then recompute the grades and see if there's a significant difference, keyword significant, between the test grades before the change and after the change, match pairs. All right, so you see that's the thing. There's a lot going into it. It's a statistical analysis, but it's an appropriate statistical analysis. And it goes a lot deeper than that question was too hard. All right, because if you look at something that you can quantify, then it takes away the guesswork, right? Because perception is a killer in statistics, all right? So when you run a study, if you allow perception to be the driving force of your statistical analysis, it's all over, all right? I mean, the only way that would actually work is if your study was on perception, all right? Because if you were to go to somebody and say, take a look at this question, you know, I randomly selected 100 people and I showed them this question and 99 of them said it was too hard. All right, cool. What made it too hard? They didn't know. Why didn't they know? Well, they were sitting in an English class and I showed them a stat question. They didn't know how to do it. Well, I guess everything's too hard. I'll tell you right now, if you gave me a writing prompt in an English class and asked me to diagnose whether it was too hard, the answer is yes, it is too hard. I would read like the first 2 words of it and be like, yes, too hard. Why? Because I'm not a writer, right? So that's just my thing. We all have our own things, but I would look at it and be like, oh, this requires me to write stuff. It really doesn't matter what the prompt is. It's too hard, right? So there are folks that are like that. I mean, you walk into a history class or a science class or whatever class, doesn't matter. You walk into the president's office. Show the president of the college. Show her a statistics question and say, what do you think? Too hard? And the answer might surprise. It might be, yeah. Oh, that looks like a doozy. Meanwhile, it could be it might be like a trick question on your end because it might be a question that you know is actually pretty easy, you know. So that could be a fun project to work with. You know, take the easiest question from this class and just show it to a bunch of random people, with the idea being that you are testing not the difficulty level of the question, but the perception of the individuals, right? I guarantee you, even the easiest question in this course will have lots and lots of people saying, too hard. How dare that professor ask that question? And you'd be like, whoa, this was a gimme on the last test. Everybody got this one right, you know, so it could be fun. I mean, it definitely would be fun. I'll enjoy it. I'm saying it could be fun for you.
It is sociologically, like you said, people can perceive it as too hard because they don't know how easy it is.
Right.
Once you point out how easy it is.
Right, and then, I mean, you could just put, like, you don't even have to put the title of the course on the top of the paper. You just make it very clear that it's a math problem, and all of a sudden people are like, too hard. You just came at me with a math problem. Like, why are you doing this to me? I was enjoying my bagel. Like, please stop, you know, so Yeah, the perception for math specifically is it's a different animal, but definitely entertaining. Some because I have my high school students doing the same project at the same time, and one of the thoughts that they came up with was to do, because I show them a video clip from Live Witness News, Jimmy Kimmel show, Jimmy Kimmel Live, which is, if you haven't seen it, it's just an interviewer going around and asking people questions with the idea that ignorant responses are often what will drive a survey, and so people don't want to look like they don't know what they're talking about. So it was funny. Maybe I'll show it later. One of the questions was, in the last year we had a lot of newsworthy events. With President Trump being impeached and kicked out of office. It was definitely a very, very trying time for our country. And then the interviewer asked the question. He said, "So where were you when you heard the news?" And the person was like, "Oh, I was watching it on TV with my friends." And then he was like, "So how did it feel when you saw President Trump being dragged out of there in chains?" And he's like, "Yeah, I gotta say, it was definitely a different kind of experience, but and he kind of elaborated on it. But when people don't know the answer to a question, sometimes they just try to fake it. And so the high school students, they want to do Live Witness News around the high school. So so that could be a thought. So if you're thinking project and you're like, because the biggest thing I've seen in the past is that people want to do projects, they're struggling for ideas. So I'll continue to throw out ideas as I think of them. If something sticks and you like it, just let me know so I can pencil you in for doing that one. Because the one thing I don't want is like I throw out an idea and everybody's doing that one idea. Because I could even say, like, you could all do like different variations of the same idea and come up with a unique product. I'm not worried about collaboration or anything like that. I'm really just worried about being bored when I'm reading your reports, because I just don't want to read the same report 17 times, right? So yeah, we'd try to vary it a little bit. Yeah, because like we talked about the Audi, versus the BMW versus the Kia versus the Honda, and again, the perception could be, like, I think the Honda drivers are the best, and the Audi, well, that whole group, just collectively, just awful. I mean, the drivers could be interchangeable. Like, you could put a Kia driver in an Audi, and I honestly think that wouldn't make a difference. But you put a Honda driver like in a Toyota, I think you're still looking at a relatively safe driver. But your perception might be completely different, and so I encourage you to prove me wrong. All right. So anyway, significance level. Cutoff probability for rejecting a true null hypothesis. It's a kind of a wordy way of explaining something pretty simple. The cutoff probability for rejecting a true null hypothesis. All right. So rejecting a true null hypothesis, I kind of missed there. So a legitimate question might be, why on earth would you reject something that's true? All right. Well, you shouldn't. All right. What we want is, we want this probability to be very small. This is just brutal. It's glitching even more than usual. We want this probability to be very small. That was an ordeal. All right. Because if you're going to reject something that's true, the chances that that's going to happen should be, I mean, it should be 0. But we'll settle for something close to 0 because data, they are what they are. You know, sometimes you have things like outliers and unusual occurrences, and so nothing's perfect. Perfect would be 0, all right? A probability of 0. Probability of rejecting something that's true, we want that to be 0, but we'll take close to 0. So the most common values that we use are, as cutoffs, 0.10, 0.05, and 0.01. Somebody a long time ago decided upon these values. In general, we want the value to be as close to 0 as possible. So regardless of what the cutoff value is chosen, the probability value, we want that to be as close to 0 as possible. So the test becomes stronger as alpha approaches 0. All right. So that alpha value again is a significance level. All right. So, just a little context here. You have a null hypothesis. This is what you're trying to either prove or disprove. The alternative is what is true if your null is not. All right. So it's either choice A or choice B. If it's not choice A, if it's not your null, it's got to be the alternative. All right. So what we do is we look at the null and we find a probability value for that null hypothesis. We use some calculations to determine that. If that probability is very, very small, then what we're going to do is we're going to say that that null hypothesis is not true. All right. And we cause that as we cause a rejection of that null hypothesis. All right. And once we decide we're rejecting that null hypothesis, it means that the alternative hypothesis must be true. All right. So really, it's just a matter of figuring out what the number. Well, we'll set up our scenarios, and I'll show you how to do that in a few minutes. But we're going to use the calculator to determine probabilities for us, and then as long as we know what that probability value corresponds to in terms of the null or the alternative hypothesis, then you'll effectively be able to draw conclusions based off of data. All right. And you'll find as we go forward, the first hypothesis test that we do, it'll seem like I'm just making stuff up on the fly. And then after we do a second one and a third one, you'll be like, oh, okay, it's the same structure. It's just what we do in the calculator is slightly different. All right. But the idea is that as we work our way through, a couple of things should start to happen. One, you start to recognize under what circumstances you use which hypothesis test, and I'll point those out as we go. But also, you should be on the lookout, like I was saying, some of you came in after I said this, you should be on the lookout for a hypothesis test that might apply to your project if you're choosing to do a project. All right, so you would say, oh, I was working with percentages. All right, so any population proportion question would apply to you. All right, so you'd start thinking about, okay, well, he's talking about apples. I was talking about cars running red lights, but I mean, structurally, it's about the same, so I think I could use that hypothesis test for my project. All right, so that's what you're on the lookout for. All right, power, type 1 and type 2 errors. There's a little formatting issue here. There should be a space. So if anybody's in the market for a typo, I dropped my pen. Cripes. There should be a space there. But the power of a test is defined as how easy it is to reject the null hypothesis. The more power the test has, to increase the power of a test, you can either do one of two things. Increase alpha, makes it easier to reject the null, or you can increase the sample size. That would make your standard deviation smaller. Type 1 and type 2 errors, they're just two ways to screw it up. Type 1 error is rejecting a true null hypothesis. Type 2 is accepting a false null. All right, so if you reject something that's true, that's pretty bad. If you accept something that's false, that's also pretty bad, but the one that's actually worse is the type 1 error, which is why it's called type 1. All right. And I'll explain a little bit more about that in a sec. So this is the worst. All right, so just going back to the definition of a null hypothesis. It's either a statement that's being tested, so that's on my end, if I'm running a hypothesis test or a study, or some understood or accepted value for the population parameter, the status quo. All right, so that's the important piece. All right, so this is what the number is. You know, so in the world, this has been the accepted value. All right, this is the number that has been in existence possibly for years. All right, so I don't know how familiar you are with physics concepts, but there is a number associated with gravity, acceleration due to gravity. It's known as the gravitational constant. Right? Depending on the units, it might be a different number, but it's generally 9.8 meters per second squared. All right. Physicists have been using this number for, I mean, as far back as physics goes. All right. This is the gravitational. This is how the Earth pulls individual molecules towards its center. All right. That's what gravitational that constant represents. Right? All of our understanding of physics is defined on planet Earth is defined based off of that number. Right? So our understanding of how objects fly through the air, how objects fall, right? How objects maintain their position relative to the ground, it's all based off of that number. So if I'm running a statistical analysis and saying that number is incorrect, I damn well better be right about it. Right, because that's like a world-changing conclusion, right? So if I make a type 1 error, I'm taking that true statement that the gravitational constant is 9.8 meters per second squared, and I'm saying it's wrong, but I'm wrong about that. I'm incorrect in making that statement, all right? So I like that. That's the worst possible outcome in a statistical analysis. You're taking something that has been a long-standing belief and you're throwing it out the window. Like it's on the same level as you've come up with evidence, conclusive evidence that the Earth is not round, right? And now you're perpetuating that information out into the real world. And bottom line is, once they figure out that you made a mistake, you're just going to look like an imbecile, all right? So that's probably the best case scenario. The worst case scenario is that the entire society falls apart because everybody makes changes based off of your calculations. Intro to stat class, I wouldn't expect that necessarily to happen, but you know, that's the consequences of making a type 1 error, all right, in the real world. All right, so it's something to be very, very careful about. All right. So yeah, and so the statement here is that alpha could be thought of as the probability of making a type 1 error, which means that if I can minimize my alpha value, if I can get that to be very, very small, then what I'm doing is I'm reducing my chances of making that critical error, all right, to the point where hopefully it's 0, all right? So if I can get that alpha value to be right around 0, then it's going to be a pretty good situation. I'll just kind of get you through the top of the next page, and then I'll kill the video and start a new one. So the p-value approach. P-value is a probability value. It's going to come from your graphing calculator. All right? This is not something that we'll have to do by hand. We're kind of done with the by hand stuff, which is good. So probability value. All right, which kind of stinks because, I mean, P is kind of meant probability for the whole course, but it's going to mean something different now, but it's still using the letter P. But we actually call it the P value. We generally don't say P as a standalone, right? We say P value. All right. And so what that is the probability of mistakenly rejecting the null hypothesis. Probability of mistakenly rejecting the null hypothesis. A simpler way of saying it would be, and this is actually not correct, but it's simple and it gets the job done. You could say the probability that the null hypothesis is true, but that's not really what it is. All right, so I'm not going to write that down because I don't really want to write down something that's just wrong in my notes and then have it out there. But as a working definition, just kind of like more like a mnemonic device sort of thing, it's really just saying that the probability of the null hypothesis being true is the p-value. All right, so. But the idea of mistakenly rejecting the null hypothesis, I mean, that's kind of a crazy thing to think about. You rejected the null hypothesis incorrectly. Like you weren't supposed to reject the null hypothesis, but you did. Right? So if that's the case, that's a bad thing. So the probability of doing something bad, we want that to be really small. All right? So this is along the same lines as alpha. And in fact, you could even think of the p-value and alpha as the same thing, except that the alpha value is the cutoff, right? It's the desired p-value. So you have a cutoff alpha value. If you're below that alpha value, you're in the safe zone. If you're above that alpha value, you're not, right? With the idea being that you want to be as close to zero as possible. Right. A lot of this is, it's hand waving and stuff. So it's like, all right, cool. A lot of words, a lot of vocabulary. What the hell does any of it mean? You don't really see it fully until you see it in action. So that's what we're going to do next. All right. We'll get into some hypothesis tests, and it'll all start to kind of flow together. All right. Yeah. So anyway, let me kill this video and start a new one. Start fresh.